All right, we're going to continue with section 15.4 in this video. And we're going to do some exercises starting on page 1028 of your textbook. We are going to start with number 3, which says in exercises 1 through 5, find the line integral over c of m of xy dx plus n of xy dy, where c is oriented counterclockwise. All right, so Green's theorem gives us two different approaches for evaluating or finding a value. We can use a line integral or we could use a double integral. If your directions say explicitly to use Green's theorem, which since we're in 15.4, they basically are saying use Green's theorem. If they say explicitly to find the line integral, using Green's theorem, they're telling you to evaluate the double integral. If they explicitly said find the double integral using Green's theorem, they're telling you to use the line integral. Because if we just evaluate the line integral they give us, we're not using anything from this section. We're just using the fact that we already know how to evaluate a line integral. So they want us to use our new approach, basically. So they give us that m is equal to xy, n is equal to x to the 3 halves plus y to the 3 halves. And they tell us c is the square with vertices 0, 0, 1, 0, 1, 1, and 0, 1. So keeping in mind that we know we're going to evaluate a double integral, we can go ahead and sketch our region, because we know whenever we evaluate a double integral, we always sketch the region over which we're integrating. So there will be some occasions in Green's theorem's problem where you may not know what your region looks like, but 9 times out of 10, if you run into a problem like that, it's because your integrand is 0. So you really don't need your region because you're going to get 0 regardless. So we'll look at an example of that later. But for now, we have our m and our n. And if we know we're going to end up evaluating a double integral, let's go ahead and sketch out the region over which we're integrating. So 0, 0, 1, 0, 1, 1, and 0, 1. All right, so now in practice, say on a test or a quiz, you wouldn't necessarily know that you were in the Green's theorem section, or you wouldn't be in the Green's theorem section. You would just have a mixture of problems there. So they told us that this is our boundary curve right here. So now with the boundary curve like that, that's a closed curve. We have some region R and it closes. So if this problem were presented to you in another section, say in 15.2, when we learn how to evaluate line integrals, in that section, we would have to evaluate a line integral over this first line, plus a line integral over that line, plus a line integral over that line, plus a line integral over that line. So when a problem like this was presented to you, you sketch your region and you decide, okay, do I want to evaluate these 4 line integrals and add them, or would I rather do one double integral over this enclosed region? Now, if you don't have an enclosed region, you don't have any choice. Say, for instance, we didn't have this top line on here, then we will be forced to do a line integral over that plus that plus that, because we don't have an enclosed region in the first place. But if your region is enclosed, now you have the option whether to do the 4 line integrals and add them together, or do one double integral. So that's why I said you do whichever one is easier. Here, it's a lot less work for us to do one double integral than it is for us to do those 4 line integrals and sum them. So we're going to use Green's theorem and just do one double integral. So what we're looking to do is evaluate the line integral over c of m dx plus n dy but we don't want to go through all that work of doing these 4 line integrals and adding them together, or these 4 line integrals and adding them together. So instead, we're going to use Green's theorem, which says this is equal to the double integral over that region R of n sub the partial of m with respect to x, minus the partial of m with respect to y dA. So we can do this instead. So now we need to look at what is n sub x and what is m sub y. So n sub x is the partial of this with respect to x. So we get 3/2 x raised to the 1/2, and then m sub y, or the partial of this with respect to y, is just x. So m sub y is just equal to x. So now we get that that line integral that we were looking for is actually just a double integral from 0 to 1 and then 0 to 1 of 3/2 x to the 1/2 minus x dx dy, or dy dx, doesn't matter which one you do first. And we all know how to evaluate that quite easily, and it's a lot faster than doing those 4-line integrals. All right, so that's one use. And notice this is different than those area formulas that I was given in the last video. So this is just a general usage of a Green's theorem. I mean, a general Green's theorem problem, whereas those other formulas were if we were trying to find the area of some region R. So we'll look at one of those a little bit later, but we're not trying to find the area. We were not given a problem that says find the area of this region, because if we were, we know that's a double integral problem, and we would just set that up and evaluate it, because this is a very easy region for us to find the area of. I mean, of course, we wouldn't use a double integral, but if our hand was forced, we know how to use a double integral. We could start with that double integral if this were an area problem of 1, and then convert it to a line integral problem using one of those other formulas. But this is not that type of problem. This is just flat out telling us evaluate this line integral, us deciding it's easier to do this, and then going that route instead. All right, so next we're going to look at number 6. So another thing to make note of is that Green's theorem is only used for line integrals of vector fields. It's not used for line integrals of scalar functions. So when you learn how to do a line integral of a scalar function and a line integral of a vector field, this is only for line integrals of vector fields, not scalar functions. All right, so in exercises 6 through 14, use Green's theorem to evaluate the line integral. Assume that each curve is oriented counterclockwise. So they already have a line integral set up for us. So line integral over C of the quantity y cubed plus y dx, y cubed plus y dx, and then plus 3y squared x dy, plus 3y squared x dy. And they told us explicitly use Green's theorem, which is saying don't evaluate this directly. Use Green's theorem to do it instead. So evaluate the double integral instead of doing this directly. All right, and they said our C is the circle x squared plus y squared equals 100. So another thing to keep in mind, it has to be a closed curve C. If it's not a closed curve C, we can't use Green's theorem. You would just have to evaluate the line integral directly. All right, so we'll just talk about how you would evaluate this line integral directly if you had to, even though we're told not to. So remember, to evaluate a line integral, you would have to parameterize this curve C. So for us, it would be x equals 10 cosine theta, y equals 10 sine theta, and theta would vary from 0 to 2 pi. We would take the y's, plug them in right there, take the derivative of x, put it right there, 3, put our y in. Remember, our y is 10 sine theta. Put our x in, which is 10 cosine theta, take dy, and then we would integrate the whole thing with respect to theta, because there would only be thetas in there, and we would integrate from 0 to 2 pi if we had to do that. So now instead we're using Green's theorem though, which says to do a double integral. So we'll go ahead and sketch our region as we usually do for double integrals. So, and they told us that this is our curve C oriented in the counterclockwise direction, but that naturally bounds a region R, which is that region right there. And now let's look at our M. The M is y cubed plus y. Our N is 3y squared x. And Green's theorem says that this integral is the same as the double integral over our region R of the partial of n with respect to x minus the partial of m with respect to y dA. So now, because we see this, we have this this double integral set up. I mean, we don't have it explicitly set up, but we have this double integral set up in terms of x and y, but then we see our regions as a polar region, so we'll switch gears and go to polar coordinates. So this is equal to, well, actually we'll write it out completely in rectangular before we go to polar. So the double integral over R of the partial of n with respect to x is going to be 3y squared, excuse me, minus the partial of m with respect to y is going to be 3y squared plus 1. dA. So we just get -1 for our integrand. So we end up with, now we're going to take this and convert to polar coordinates, which our radius r goes from 0 to 10 and our theta goes from 0 to 2 pi. So 0 to 2 pi, 0 to 10 of -1, but we convert it to polar, so we need our Jacobian. So we have -r dr d theta. And that integral is a lot neater than the integral we would end up with if we were to evaluate this directly using a line integral with a parameterization of that curve. All right, so we'll stop there in this video, and then we'll continue with section 15.4 in our next video.